In 2017, there was this Silicon Valley startup.
Oh, I know exactly where you're going with this.
Right. So they burned through $120 million of venture capital, and they used it to build a countertop machine that basically just squeezed juice out of a proprietary bag.
120 million. Just let that number sit for a second.
It's staggering. I mean, it was this marvel of modern engineering. Yeah. Right. It had hundreds of custom machine parts. It had a Wi-Fi connection for some reason, and it cost $400.
Yeah, $400 juice press.
Exactly. But then, a few months after they launch, investors and consumers realized this really glaring detail.
The bag detail.
Yeah, the bag. You could literally just take their proprietary bag of pre-diced fruit, squeeze it with your bare hands, and pour the juice into a glass faster than the machine could actually do it.
It is, without a doubt, arguably the most expensive lesson in modern product design history. I mean, they engineered this flawless solution to a problem that simply, well, it just didn't exist.
It didn't exist at all. That is the Juicero story. And it perfectly frames what we're getting into today. So welcome to this deep dive. Today, we are tearing apart the brutal, unforgiving reality of product design.
It really is unforgiving.
It is. We are looking at a massive stack of sources today. It's essentially a comprehensive blueprint on designing your first product. We're going to figure out how incredibly smart people make $100 million mistakes. And more importantly for you listening, how you can avoid making them.
Right. Right, because taking a vague idea in your head, turning it into a physical object or a live piece of software, it's not just a matter of waiting for some magic light bulb moment.
No, not at all.
It's this high-stakes obstacle course. You're dealing with psychology, mechanical engineering, code architecture, and unit economics. It's intense.
And the sources we have today, they don't just cover one little corner of the tech world, which I love. We're looking at the entire spectrum of human creation here.
It's a whole map.
Yeah. So whether you're listening to this because you're trying to, bootstrap a Microsoft tool on your weekends, or maybe you're tasked with prototyping a new consumer gadget at a hardware startup.
Or even if you just want to understand the invisible mechanics behind the stuff you use every single day.
Exactly. This is the ultimate map of that territory.
And the intention here is to really bridge that gap between the purely theoretical whiteboard sessions, the fun part, and the deeply practical realities of supply chains and server costs.
And human behavior, which is the wildest variable of all. To do that, I've got the perfect guide sitting across from me. Someone who can navigate both the delicate psychology of figuring out what users actually want and the cold, hard realities of manufacturing and coding.
Well, I'm excited. We have a lot of ground to cover.
We do. So let's start right at the genesis point, which is the idea. The sources point out this massive flashing red warning sign before you write a single line of code or sketch a blueprint. They call it the trap of the great idea.
Right. And it's a trap because most founders just completely fall in love with an idea. But if you look closely at the data from failed startups, those ideas are almost always just solutions searching desperately for a problem.
Searching for a problem that isn't there.
Exactly. The sources argue that a true product idea shouldn't start as a product at all. It really should start as an observation of what they call unarticulated user friction.
Unarticulated user friction. So, meaning the user is annoyed or struggling, but they haven't explicitly asked for a specific product to fix it.
Yeah, they don't know what the fix is. They just know they're in pain.
So how do you find a problem that people can't even articulate?
You have to completely change how you view consumer behavior. And the first framework the sources provide for this is called jobs to be done, or JTBD.
Okay, JTBD.
The core premise here is that people do not buy products. They hire them to do a job in a specific circumstance.
Oh, this is like the classic drill bit example, right?
Yes, exactly.
Where it's like, nobody actually wants to own a quarter-inch drill bit. They want a quarter-inch hole in their wall.
That's the surface level of it, yeah.
Yeah.
But if you apply the framework deeply, like really dig into the psychology, you realize they don't even want the hole in the wall.
Wait, they don't?
No. They want to hang a framed photograph of their family so they can feel a sense of warmth and belonging in a new apartment.
Oh, wow. Okay.
Right. So the job they are hiring the drill bit for has a functional component, making a hole, but it also has this massive emotional component, which is creating a home.
Okay, I get that. But if I'm the person manufacturing that drill bit in a factory, why does it matter if I know they want to feel warmth in their apartment? I mean, isn't a drill bit just a piece of metal?
It matters entirely because it redefines your competition.
How so?
Well, if you think the job is just making a hole, you're going to spend all your R&D money trying to make a sharper, faster, cheaper drill bit. You're trying to compete with other hardware companies.
Right. DeWalt versus Makita.
Exactly. But if you realize the actual jaws is hanging a picture without stress, you suddenly realize your biggest competitor isn't another drill company at all.
It's someone else entirely.
It's a company making damage-free adhesive wall strips.
Oh, like command strips. That completely changes the perspective.
Right. The adhesive strip gets hired for the exact same job, but it requires zero power tools, it creates zero dust, and it doesn't risk your security deposit.
And if you're stuck in that solution mindset of just making better drill bits, the adhesive strip basically blindsides you and steals your market share.
Exactly. Jobs to be done forces you to ignore your proposed solution and just obsess over the friction the user is experiencing. But, identifying the job is only step one.
Right.
The sources are very clear that you then have to validate if that friction is actually painful enough that someone will pay you to remove it.
Which brings us to this concept called the MOM test. And I have to admit, when I first read about this in the sources, it felt a little bit cynical to me.
It sounds cynical, but it's really just human nature.
Yeah, because the premise is essentially that everyone you talk to about your idea is going to lie to you.
And it's not malicious lying. I mean, it's just social conditioning. Humans are generally conflict averse.
Right, we want to be nice.
Exactly. If you walk up to a friend or, your mother and say, hey, I have this incredible idea for a new recipe app that curates meals based on what's in your fridge, would you use that?
Their immediate instinct is to support you.
Right. They're going to say, oh, that sounds amazing. I would totally download that.
And then, based on that feedback, you go spend $50,000 in 6 months of your life building it. You launch it, you send them the link, and it's just crickets. They never open it.
Because you ask them a leading question about their future intent. And people are terrible at predicting their future behavior.
We're so optimistic about who we're going to be tomorrow.
They imagine this idealized version of themselves, the version that cooks healthy, curated meals every single night.
So how does the MOM test actually work then?
It dictates a strict rule. You never, ever mention your idea during the validation phase. You only ask questions about the user's past behavior.
Okay, so instead of pitching the app, what do I say?
Yeah.
I just asked my mom to tell me about her dinner routine this past week.
Precisely. You ask, hey, how did you decide what to cook for dinner last Tuesday? Did you look up any new recipes in the last month?
And if she says, honestly, no, I just cycle through the same 5 meals from memory because I'm too tired after work to think about it.
Then you instantly have your answer.
Wow.
The job of finding new recipes isn't an actual pain point for her. The real friction is fatigue.
So regardless of how much she praised your app idea in the hypothetical scenario, her past behavior proves she wouldn't use it.
Exactly. You extract the truth by observing history, not by asking for permission.
It's like being a detective instead of a salesperson. You're looking for evidence of the crime, the friction, rather than asking if someone plans to commit a crime in the future.
That's a great way to put it.
And the sources provide a massive case study on this kind of behavioral validation, which is Airbnb.
Airbnb is perhaps the most profound example of validating unarticulated friction in the last couple of decades.
Because most people just assumed the problem Airbnb solved was hotels are too expensive.
Right, but if that were the only problem, they could have just built a discount hotel aggregator like Kayak or Expedia.
Right.
The actual friction they were tackling was much deeper. They were attempting to build a system where a person would feel safe sleeping on an air mattress in a total stranger's apartment.
Which sounds insane when you say it out loud.
It does. The unarticulated friction wasn't pricing, it was trust.
So how do you validate trust without building the whole platform? Because you can't just ask people, would you trust a stranger?
You observe behavior. In their earliest days, they didn't have massive safety algorithms or identity verification APIs. They literally went door to door in New York.
Just walking up to apartments?
Yes. Meeting the hosts in person, taking professional photos of the apartments to make them look legitimate, and establishing a baseline of human connection.
Wow.
They had to prove that the job of feeling secure in a stranger's home could be fulfilled through digital profiles and user reviews. They were validating human psychology, not software mechanics.
And then you compare that deep psychological validation to the Juicero disaster we opened with. Juicero just skipped the problem validation entirely. They just assumed people hated squeezing juice.
Juicero is what happens when you substitute engineering for empathy. They fell in love with the mechanics of the machine. They built a solution in a total vacuum.
Which really highlights a stark dividing line in our sources regarding the nature of the product you're building. The risk profiles for digital versus physical products are fundamentally different right from the validation stage.
Oh, absolutely. Night and day.
Because if Juicero had been a software app, failing would have cost them a few months of developer time. But because it was physical hardware, failure cost over $100 million.
The sources outline two distinct paths here. For digital products, software, apps, platforms, you typically operate on a stage gate idea process.
Stage gate, meaning it's in phases.
Right. Code is malleable. You can build a tiny, rough version of the software, put it in front of users, get feedback, and then use that data to unlock the next gate of funding or development time. It's highly fluid.
You could pivot instantly. But the physical path is rigid. The sources introduce these acronyms like BABOM and DFM right at the idea stage.
Yeah, those are terrifying acronyms for hardware founders.
So if I'm designing a new piece of hardware, say a smart thermostat, I can't just sketch it on a napkin and figure out the insides later.
Absolutely not. Physical validation requires you to immediately consider the bill of materials, or the BOM.
Every single part.
Every single microscopic screw, every resistor on the circuit board, the specific type of plastic for the casing, it all carries a fixed cost. You have to know the BOM before you can even determine if the business is viable.
Because if the parts cost more than people will pay, you're dead on arrival.
Exactly. And furthermore, you have to consider design for manufacturability, or DFM.
Meaning, can a factory actually make the thing you drew?
Precisely. You might use a 3D modeling program to design this stunning, seamless, curved glass casing for your thermostat. It looks beautiful on screen.
But then reality hits.
Right. You take that file to a factory in Shenzhen, and the engineers tell you that injecting molten plastic into that specific shape will cause it to crack 40% of the time as it cools.
40%.
Yeah. So your beautiful design is worthless, and you cannot release a software patch to fix a broken plastic mold. The physics have to be validated right alongside the market demand.
It's so unforgiving. And this tension of validation brings up a fascinating debate that's highlighted from Reddit's startup communities in the sources. It's the classic paranoia of the first-time builder. Idea secrecy versus execution speed.
Oh, I see this all the time.
Right. Someone has an idea and they refuse to tell anyone about it unless they sign a non-disclosure agreement, an NDA, just to have coffee.
It is the most common symptom of a novice founder. They're absolutely terrified that if they use the mom test or talk to potential users, someone is going to steal their billion-dollar idea.
But the sources and the consensus in these technical communities, they basically argue that this secrecy is suicidal for a new product.
It is, because an idea in isolation has effectively zero economic value.
None at all.
The execution of the idea is where all the value is created. The feedback you gain from openly discussing and validating the friction far outweighs the infinitesimally small risk that a person you're talking to is going to, drop their entire life, quit their job, secure funding, and execute your unproven concept better than you.
It's just ego to think someone cares that much about your idea.
Exactly. Operating in stealth mode usually just ensures that you build a Juicero. A secret perfectly kept right up until the moment it fails spectacularly. Execution speed, fueled by open feedback, is your only real moat.
Okay, so let's assume we've navigated this trap. For the sake of the listener, you've thrown away your secrecy, you've observed past behavior, you've found a real bleeding neck problem that people are desperate to hire a product to solve.
Awesome. You're past step one.
But the next reality check hits immediately. You cannot build this alone. You need a team. And pulling together a founding team seems to destroy companies faster than bad ideas do.
Moving from the abstract idea to the concrete execution is where the human element takes over. And the courses emphasize that the overarching success of a product is almost entirely dependent on the psychological alignment of the people building it.
It's basically the highest stakes group project imaginable.
It really is.
The sources reference a psychological framework for this called the dating and trial sprint model. I really want to dig into this because the default behavior for most people is to just grab a friend, say, hey, let's start a company, and immediately incorporate and split the equity 50-50 on day one.
Which is a mathematical recipe for resentment.
Why is it so dangerous?
Because you are legally and financially chaining yourself to an individual you have likely never observed in a high-stress, high-stakes environment.
Right.
You might be great friends at a dinner party or play golf together, but how does that person react when a server crashes at 2 a.m. and you are losing thousands of dollars an hour?
Do they panic or do they fix it?
Exactly. The trial sprint model changes that dynamic. It mandates a probationary period.
Before any paperwork is signed.
Before any equity is assigned, before the company even officially exists, you agree to a strictly bounded project, like a 4-week sprint to build a basic prototype or conduct a massive market research project.
It's a corporate test drive.
Yes,
Right.
and it is entirely about observing their behavior, much like the mom test. Do they meet their deadlines? How do they handle constructive criticism?
Because there will be criticism.
Always. When you inevitably disagree on a feature, does it turn into a screaming match or productive debate? You are validating the co-founder relationship before you validate the product.
But it's not just about getting along, right? It's about having the right mix of skills. The sources bring up this archetype model, the holy trinity of early-stage building. The hacker, the hustler, and the designer.
Ah, yes, the classic trio.
So the hacker writes the code or engineers the physics. The designer ensures that the user can actually understand it. And the hustler sells the vision, talks to users, and secures the funding.
It's a foundational model that balances 3 necessary forces: technical reality, human empathy, and commercial viability.
I have to challenge this, though. I mean, is this clean 3-person division actually realistic outside of a textbook?
It's a fair pushback.
Because what happens if it's just 2 people? Or, what happens when the hustler, the visionary who wants to promise the world to investors, demands a feature by Friday, and the hacker looks at them and says, if we do that, the database architecture will literally collapse. It seems like setting up these distinct roles is just designing a cage match.
It is a cage match, but that friction isn't just realistic. The sources argue it is structurally necessary.
Necessary. Why?
If you look at the hacker news threads referenced in the text, this dynamic is a daily reality. Think about the failure states if one of these forces wins completely.
Okay, let's walk through that.
If the hustler has total control, you get vaporware.
Just marketing hype for a product that doesn't actually exist.
Right. And if the hacker has total control, you often get a flawlessly architected, incredibly fast back-end system that solves a problem no normal human being cares about, with a user interface that looks like an Excel spreadsheet.
I've used that software before.
Yeah.
It's terrible. And if the designer has total control,
You get a beautiful, stunning piece of art that takes 10 years to build and has absolutely no business model.
okay, so you need the tension.
Precisely. The friction is the mechanism of balance. You need the hustler pushing the team to move faster than is comfortable. You need the hacker pulling the emergency brake when structural integrity is at risk. And you need the designer constantly reminding both of them that a human being actually has to use the thing. It is about cognitive diversity.
And the sources ground this in 2 really contrasting case studies. Let's look at a healthy execution of this first, which is Canva.
Canva is presented as the absolute gold standard of domain-separated leadership.
How do they structure it?
Well, Melanie Perkins, the visionary CEO, was obsessively focused on the overarching goal of democratizing design. She owned the empathy and the market need. She was the designer and the visionary.
Oh.
Her co-founder, Cliff Obrecht, operated as the operational engine, the hustler managing the business mechanics, the partnerships, the growth. And their technical co-founder handled the immense complexity of making a robust design tool run smoothly inside a standard web browser, which was incredibly hard to do at the time.
So they had distinct lanes, and they respected the authority of the person in that lane.
Exactly. When a technical dispute arose, the hacker had the final say. When it was a user experience issue, Perkins had the final say. The trust they built during their early days allowed them to defer to each other's expertise without ego getting in the way.
Now contrast that with the cautionary tale of Zipcar provided in the text. I mean, Zipcar eventually became a massive success, but their early days were defined by toxic friction.
Because their equity and authority were misaligned from the start.
What happened?
In Zipcar's early phase, the internal battles over who actually owned specific product decisions, combined with an early equity structure that didn't reflect the actual output of the founders, led to really deep resentment.
So they were fighting over who was in charge instead of building.
Right. When the technical architect and the commercial visionary are spending all their energy fighting for control of the roadmap rather than trusting each other, feature delivery stalls. The product development process effectively grinds to a halt while the founders play politics.
Which proves exactly why that initial 4-week dating sprint is so critical.
Yeah.
You have to find out if you're working with someone who wants to build a product or someone who just wants to be a boss. Okay, so we have the unarticulated friction. We have a balanced, battle-tested team. Now we have to figure out what exactly we are going to build and where it fits into the world.
Right, because before any metal is cut or any code is committed to a server, the team has to position themselves strategically. You have to map the ecosystem you're about to enter.
And the sources rely on the blue ocean strategy for this, specifically mapping a strategy canvas. The metaphor here is incredibly vivid. It says most markets are red oceans.
A red ocean is a mature, crowded market.
Like smartphones.
Exactly. Think about the smartphone market today or the CRM software market. It is full of giant incumbents fighting viciously over the exact same pool of customers by offering microscopic improvements. The water is red with the blood of competition.
And competing there requires massive capital.
Almost impossible for a startup.
So the goal is to find a blue ocean, an uncontested space. But how do you actually map that out using a strategy canvas?
You literally draw a chart.
Okay, visualizing a chart.
On the bottom axis, you list every single factor that the current industry competes on. Price, speed, number of features, customer service. Then you plot the major competitors. You'll usually see they all have very similar shapes on the graph.
They're all trying to max out the same features.
Right. A blue ocean strategy requires you to look at that graph and intentionally choose to offer drastically less of what the industry standard is in exchange for offering something completely new that the incumbents are ignoring.
You find their blind spots. And the sources highlight a massive real-time example of this happening right now with the rise of AI.
The great unbundling of legacy enterprise software. It's fascinating.
It is wild to watch. You have these massive multi-billion-dollar software suites that large corporations use. These platforms do 100 different things: HR, payroll, project management, expense tracking.
But because they do 100 things, they do most of them poorly.
Exactly. They are clunky, slow, and universally hated by the employees who have to use them.
They are the ultimate red ocean incumbents. And they are too massive and slow to natively integrate artificial intelligence into their core architecture quickly.
So small, agile teams of 3 or 4 people are looking at these giant suites, picking just one specific feature, let's say expense report filing, and building an AI-native microsauce tool that does only that one thing, but does it flawlessly, instantly, and automatically.
They are executing surgical strikes on the blind spots of the behemoths. They don't try to replace the whole suite, they just carve away the most frustrating piece of the user experience. That is a blue ocean within an existing market.
And this vast difference in approach between building a tiny AI tool and building a massive enterprise platform, it really highlights the sheer scale of the blueprint we're examining today. The sources detail a landscape of 25 distinct product types.
It's a huge landscape.
I think we need to contrast a few of these because the phrase product design means entirely different things depending on the domain.
The sources divide the universe broadly into digital tech products and asset-heavy physical products, and the development cycles couldn't be more different.
Let's take 3 completely different examples from the text to see how the mechanics shift. Let's compare a B2B SaaS application, an autonomous ag tech harvester, and a medical device implant.
A perfect spectrum of risk.
Right.
With the B2B SaaS application, let's say it's a project management tool, the capital requirement is relatively low. Your primary costs are developer salaries and cloud hosting.
And what about regulations?
Your regulatory burden is mostly centered around data privacy, like GDPR compliance. If you push a bad update and the software crashes, users are annoyed, you lose some productivity and maybe some revenue, but you can usually roll back the code in minutes.
So the blast radius of failures contain mostly to screens and spreadsheets.
Exactly. Now shift to the autonomous ag tech harvester. This is heavy industrial machinery infused with deep tech computer vision.
A 20-ton robot driving through a cornfield.
The capital requirement jumps from thousands to tens of millions. You are dealing with complex supply chains for steel, sensors, and powertrains.
And the risk of failure.
If your software has a bug here, you don't just get an error screen. The harvester might drive through a barn, destroy a season's worth of crops, or severely injure a human operator. The regulatory burden shifts into heavy machinery safety certifications and environmental standards.
And then the far end of the spectrum, the medical device, an implantable pacemaker.
Here, the barrier to entry is astronomical. It is governed by rigorous bodies like the FDA in the US or CE marking in Europe. You cannot use the stage gate fluid testing model on humans.
You can't just launch a buggy pacemaker and patch it later.
No. The product must be near perfect before it ever touches a patient. The risk isn't just financial or property damage, it is human mortality.
And the sources introduce an engineering framework specifically designed to handle these extreme physical risks before the product is even built. It's called FMEA, Failure Mode and Effects Analysis. How does this actually work in practice?
FMEA is basically a highly structured mathematical approach to pessimism.
I love that. Mathematical pessimism.
You gather the engineering team, and you systematically list every single component of the product. Let's take a simplified example, like a commercial coffee maker. You look at the heating element. You ask, what is its failure mode?
It overheats and doesn't shut off.
Right. Then you score 3 variables on a scale of 1 to 10. First, severity. If it overheats, what happens? It could start a fire. That's a 9 or a 10 on severity.
Okay, 10.
Second, probability. Based on the component's lifespan, how likely is this to occur? Maybe it's a cheap part, so probability is a 6.
Okay, 10 and 6.
Third, detection. What is the likelihood that our factory testing will catch this specific flaw before it ships to a customer? If it's hard to test for, detection might score an 8, meaning it's highly likely to slip through.
So you have a severity of 10, a probability of 6, and a detection failure of 8.
You multiply those together to get a risk priority number, or RPN. 10 times 6 times 8 is 480. You calculate this for every single part.
Okay, what if a button on the front panel just gets stuck?
Let's run the math. Severity is maybe a 2. It's annoying, but it's safe. Probability is a 3. Detection failure is a 2 because a visual inspection catches it easily. The RPN is 12.
So it forces the team to rack and stack the disasters. You don't spend time re-engineering the sticky button until you have completely redesigned the heating element with a thermal fuse to drop that 480 score down to a safe level.
Exactly. You pair that with QFD, quality function deployment, also known as the house of quality.
What does that do?
This is a matrix that takes the subjective things a customer wants, like I want the coffee maker to be quiet, and forces the engineers to attach hard, measurable specifications to it, like the pump decibel level must not exceed 50 dB.
It ensures that safety requirements and user empathy are hard-coded into the blueprint simultaneously, which provides a beautiful segue for us. We've mapped the market, we've mathematically prevented the coffee maker from exploding using FMEA, but none of that matters if the user can't figure out how to turn the coffee maker on.
Right, the user experience.
We have to translate these engineering specs into an actual human experience.
This bridges the gap between understanding the mechanics and interacting with the human mind. The sources lean heavily on empathy-driven design, specifically targeting a concept called cognitive load.
Cognitive load. So that's essentially the amount of mental processing power required to figure out how to use your product.
Exactly. Every time a user has to pause and think, wait, what does this icon mean? Or where did the checkout button go? Their cognitive load spikes.
And we don't like to think.
Our brains are inherently lazy. We want the path of least resistance. If the cognitive load is too high, the user will just abandon the software. Or, in the physical world, the factory worker will bypass the safety protocol on a machine because it's too complicated to use.
The sources cite Nielsen's 10 usability heuristics as the golden rules for reducing this load. These are basically the laws of interaction design. My favorite one to think about is visibility of system status.
It is arguably the most important heuristic on the list. A system should always keep users informed about what is happening in a reasonable time frame.
Think about the pure anxiety of uploading a massive file to a website or submitting a payment, and the screen just goes completely blank.
Oh, it's the worst feeling.
There's no spinning wheel, there's no progress bar. You just sit there for 30 seconds wondering, did it work? Did I just get charged twice? Do I hit refresh and ruin everything?
That is a massive spike in cognitive load caused entirely by a lack of visibility.
But a simple animated progress bar completely removes that anxiety.
Right. The machine is telling the human, I hear you, I am working on it, please wait.
This relentless focus on removing friction and reducing cognitive load leads to one of the most famous pivot stories in tech history, the origin of Slack.
It's an absolute masterclass in recognizing where you have accidentally solved a massive problem.
Because most people assume Slack was founded by a team trying to disrupt corporate email. But Stuart Butterfield and his team were actually trying to build a massive multiplayer online video game called Glitch.
It was highly complex, creative, and ultimately it was failing. They couldn't find product market fit for the game.
But because their development team was distributed across different cities, they needed a way to communicate constantly. Email was too slow, and standard chat rooms were too disorganized.
So they built their own internal tool based on old IRC internet relay chat protocols.
They built a tool purely to solve their own internal friction. They needed to share code snippets, search past conversations, and organize by channels without the cognitive load of a massive email inbox.
And as the video game was dying, they realized something profound.
What was it?
The game was a failure, but the internal communication tool they had built to support the game was the smoothest, most frictionless piece of software they'd ever used.
They realized the job of corporate communication was broken, and they had accidentally built the perfect adhesive strip while trying to invent a new drill.
Exactly. They scrapped the video game, polished up the chat tool, and launched Slack. It's a testament to letting the user experience dictate the product's value rather than forcing your original vision on the market.
So how do we actually start testing these experiences? How do we build the first version without going bankrupt? The sources break down the prototyping spectrum, which looks very different for digital versus physical products.
Let's start with digital. The spectrum begins at 0 fidelity, a napkin sketch.
Literally drawing boxes on a piece of paper.
It is the cheapest, fastest way to see if the flow of screens makes logical sense. From there, you move to lo-fi wireframes. These are digital, but they are intentionally grayscale. No colors, no fancy fonts, no images.
Why intentionally ugly? I always wondered that.
Because if you put a beautiful, fully colored design in front of a test user, they will spend 10 minutes giving you feedback on the shade of blue you chose, rather than noticing that the checkout process is completely broken.
Oh, that makes so much sense.
Grayscale forces the conversation to remain on the structure and the cognitive load.
Once the structure works, you move to interactive prototypes. So it looks like a real app. You can click the buttons on your phone, but it's just smoke and mirrors. There is no actual database behind it.
Right. And the velocity at which teams can generate these high-fidelity prototypes today is staggering. The sources note a massive shift driven by generative AI.
Tools like Juicero.dev and Figma AI, they are collapsing the design-to-code timeline.
You don't even need to draw the boxes anymore.
You just type a prompt, you tell the AI, generate a dashboard for an inventory management system featuring a sales graph, a low stock alert table, and a dark mode toggle. And in 10 seconds, it generates the actual front-end code and a functional user interface.
What traditionally took a UX designer and a front-end engineer a week of back-and-forth iteration can now be prototyped in an afternoon. The barrier to generating digital tests is effectively 0.
But the barrier to physical prototyping is a massive concrete wall. When you shift to hardware, you enter a much more tactile and punishing spectrum.
You can't prompt an AI to instantly materialize a new titanium bicycle frame. Not yet, anyway. Physical prototyping usually begins today with 3D printing. You print complex geometries in cheap plastics or resins just to check the form factor.
Does it fit in the hand? Are the buttons reachable?
Once you need to test the actual structural integrity, you move to CNC machining, where a computer-guided drill carves the part out of a solid block of aluminum or steel.
And before you commit the massive capex for steel mass production molds, you might use silicone molds or soft tooling.
Right. This allows you to pour a few dozen units in the actual production-grade plastic to test the real-world feel.
And the sources outline the gauntlet that these physical prototypes must survive. It's governed by 3 acronyms: EVT, DVT, and PVT, the life cycle of hardware validation. Let's walk through this gauntlet because it sounds brutal.
Stage 1 is EVT, engineering validation testing. This answers the most basic question. Does the core physics of this idea actually work?
So it doesn't matter what it looks like at this stage.
Not at all. It might be a mess of wires duct taped to a piece of plywood. If you are building a new type of blender, EVT just tests if the motor can spin the blade fast enough to crush ice without catching fire.
If the physics hold up, you lock the engineering and move to DVT, design validation testing.
And this is where it gets incredibly stressful.
Why is it so stressful?
Because now the product has to work and look like the final manufactured item. It has to fit perfectly inside that beautiful casing the designer created. This is where you conduct environmental stress testing.
Dropping it and baking it.
Yes. You bake it in ovens to test thermal limits. You drop it onto concrete from 6 feet. You test the waterproofing.
And the psychological toll here on a team is immense. If the plastic casing shatters during a DVT drop test, you can't just change a line of code like you can in software.
No, you might have to redesign the internal chassis, remachine the prototypes, and delay the launch by 3 months. It's agonizing.
Once you finally pass DVT, assuming you do, you reach PVT.
Yeah.
Production validation testing.
At this stage, you are no longer testing the product, you're testing the factory.
Can the assembly line actually put this thing together?
Exactly. Can human workers or robotic arms assemble this unit quickly, consistently, and without breaking it? You do a small pilot run of maybe 100 units on the actual assembly line to validate the manufacturing process.
The sheer perseverance required to survive this physical cycle is perfectly illustrated by the James Dyson case study in our text.
The creation of the Cyclone vacuum cleaner.
Dyson spent 15 years in a shed, manually building 5,127 physical prototypes, over 5,000 iterative cycles.
And the feedback loop was agonizingly slow. He would build a cone, test the airflow, realize it failed, and have to physically construct a new cone with a slightly different angle.
Yeah.
He couldn't bypass the physical reality.
That is the traditional burden of hardware development. But the sources provide a modern contrast that is completely upending this paradigm, which is Tesla.
Right, Tesla builds incredibly massive, dangerous, highly regulated hardware, but their iteration strategy is almost entirely software-driven.
How do they do that? Traditional automotive companies lock in a physical design during the PVT stage, and that car remains statically the same for a 5-year model run. If they want to change how the suspension feels, they have to engineer new physical shocks for the next model year.
Tesla approaches a car as a hardware shell designed to deliver a software experience. They over-engineer the physical platform, putting in an excess of sensors, cameras, and computing power, and then they constantly push over-the-air or OTA software updates to change how the physical hardware behaves.
They can tweak the regenerative braking algorithm, change the suspension dynamics, or upgrade the self-driving capabilities while the physical car is sitting in your driveway.
They have effectively blurred the line between the rigid DVT hardware cycle and the fluid digital stage gate process.
It is a brilliant de-risking of the physical product. Now, when it comes time to scale up and actually manufacture these physical objects, the sources clarify the different strategic models a company can use. The alphabet soup of manufacturing: OEM, ODM, and contract manufacturing.
Let's decode these, because your asset strategy dictates how much of the factory you actually control. Let's start with OEM, original equipment manufacturer.
Okay, OEM. What is that?
This is a component play. An OEM is a factory that makes specific parts or subsystems that you purchase and integrate into your larger product.
So, for example, Apple doesn't manufacture the camera lenses in the iPhone. They buy them from an OEM like Sony, who specializes purely in optics, and Apple integrates it.
Correct. Now, contrast that with ODM, original design manufacturer. This is when a factory has already done all the engineering and design for a complete product. They have a fully functional, generic Bluetooth speaker ready to go.
So you just buy it from them.
You go to them, pick a color, pay them to print your brand's logo on the front, and you sell it as your own. You did no design work. You are purely a marketing and distribution layer.
This is how a massive percentage of Amazon brands operate. They are just white labeling ODM products. Okay, then you have contract manufacturing.
This is when you own the intellectual property. You have the exact blueprints, the BM, and the DFM analysis. You hire a massive factory operator, like Foxconn, to build your specific design to your exact standards. You leverage their labor and assembly lines, but it is entirely your product.
And the final option is owned plants, where you take on all the capital expenditure yourself. You build the building, buy the robotic arms, and hire the workers. It gives you total control, but immense financial risk.
Right. And the sources also note a massive geopolitical shift happening in manufacturing right now. The China Plus One strategy.
What's driving that?
Well, for decades, the default strategy was to consolidate all manufacturing in specific hubs in China due to efficiency and scale. But recent global supply chain shocks, pandemics, trade wars, shipping canal blockages proved that relying entirely on a single geographic point is an existential vulnerability.
So companies are maintaining their core manufacturing in China, but intentionally standing up a +1 secondary supply chain in a different region, like Mexico for nearshoring to the US or Vietnam or India.
It costs more upfront, but it acts as an insurance policy against global disruptions.
Okay, so we know how we're going to prototype it, and we know who is going to manufacture it. But here's the heartbreaking reality that every founding team eventually faces. You cannot launch your entire grand vision on day one.
You will run out of time and you will run out of money.
You have to decide what makes the final cut. Which brings us to scoping the MVP.
The brutal art of feature triage. A product roadmap is really just an exercise in saying no to good ideas.
And to prevent founders from just arguing based on gut feelings, the sources provide prioritization frameworks to make the process objective. Let's look at the RICE model.
RICE is a scoring system. Reach, impact, confidence, and effort.
Imagine you have a whiteboard with 20 incredible features you want to build. You take feature number 1 and you score it. Reach. How many of your total users will actually encounter this feature in a given month?
If it's a niche settings toggle, the reach is low. If it's a change to the login screen, the reach is 100%.
Then, impact. If they do encounter it, how much will it actually improve their experience or drive revenue? A cosmetic change might have high reach but low impact.
Next is confidence. I love this one because it checks our ego. How sure are we that our estimates for reach and impact are actually true? Do we have user data to prove it, or is the hustler founder just guessing?
You take the product of those 3 reach times impact times confidence, and you divide it by the final factor, effort.
How many rakes of engineering time will this take to build?
Exactly. The RICE score gives you a mathematical hierarchy. A feature that the visionary founder loves might have a massive impact. But if the effort requires 6 months of complex back-end coding, its overall RICE score might be lower than a simple one-day UI fix that removes a massive cognitive block for thousands of users.
It completely removes the emotion from the prioritization.
The second framework is even more ruthless. The Moscow method. Must have, should have, could have, won't have.
It forces strict categorization for a specific launch window.
The emotional pain of this framework is entirely centered on the won't have bucket. It requires immense discipline for a team to take a feature they conceptually love, look it in the eye, and agree, we are not building this for the launch.
But that discipline is what dictates the shape of the launch vehicle. It defines the MVP, the minimum viable product.
Now, the sources make a critical intervention here regarding digital products. They introduce the concept of the MLP, the minimum lovable product, as a corrective measure to how the MVP has been abused in the industry.
Yeah, in software, the term MVP became a crutch for launching terrible, buggy products. Founders would release a broken app and say, don't worry, it's just the MVP, we're iterating.
But users don't care about your iteration philosophy. They care if the product works.
The MLP argues that yes, the scope of features must be minimal, but the execution of those few features must be flawless, beautifully designed, and actually solve the friction in a way that delights the user. You can't validate a problem if the solution is too buggy to use.
And in the physical realm, the text introduces the hardware equivalent, the MVB, or minimum viable batch.
Because you can't just 3D print one pair of sneakers and sell it globally to test the market.
Exactly. For consumer packaged goods or hardware, you have to initiate a factory production run. The MVB is the calculation of the absolute smallest quantity you can produce that allows you to test the unit economics and the real-world logistics without bankrupting the company.
If the factory minimum order quantity is 50,000 units, but your MVB budget only allows for 500, you have to find a different prototyping strategy or a different manufacturing partner.
The case studies the sources provide on scoping are incredible because they show how creative you can get with an MVP. Let's look at the digital side first with Buffer, a social media scheduling tool.
Buffer is the ultimate example of validating demand with an MVP that is barely a product at all.
What do they do?
The founder had an idea for an app that would let you load up a bunch of tweets and schedule them to post throughout the day. But writing the back-end integration with the Twitter API to reliably do that was going to take a lot of effort.
So rather than building it, he built a 2-page static website. Page 1 simply explained the value proposition. Choose times to tweet, add tweets to your buffer, and we do the rest. And it had a button that said, plans and pricing.
It takes a certain level of audacity to ask people to look at pricing for a product that does not exist.
But that was the test. If users read the value prop and ignored the pricing button, he knew the problem wasn't painful enough. But if they clicked the pricing button, it showed real commercial intent.
When they clicked it, they were taken to a second static page that basically said, hello, you caught us before we are ready. Enter your email to be notified when we launch.
He collected a massive list of highly qualified leads and validated the exact pricing model they were willing to accept, all without writing a single line of back-end product code. It was a flawless execution of risk mitigation.
Contrast that digital smokescreen with a physical MVP. The sources highlight Warby Parker. They're a massive eyeglasses empire today, but their start was incredibly manual.
Warby Parker identified the friction in buying glasses online. People need to physically try them on their face before buying. The solution to this is a massive automated logistics facility that can seamlessly ship out trial boxes, track returns, and manage inventory.
Building that infrastructure would require millions of dollars in CapEx.
So their MVP bypassed the infrastructure entirely. They built a slick, Highly functional front-end website. The user experience felt like a massive, sophisticated company. You clicked a button to order a home try-on box.
And what happened behind the scenes?
Pure, unscalable manual labor. The founders were sitting in an apartment, manually packing cardboard boxes with glasses, printing shipping labels on a desktop printer, walking them to the post office, and tracking the entire complex return logistics on a single Excel spreadsheet.
It's the Wizard of Oz MVP. The customer sees a magical automated machine, but it's really just a frantic founder pulling levers behind a curtain. They manually absorbed the friction to validate that the market actually wanted the service before they spent the millions to build the real machine.
But we cannot discuss MVP scoping without looking at the dark side. The sources point to Theranos as the ultimate structural failure in this regard.
We talked earlier about the danger of idea secrecy and the necessity of peer validation. Elizabeth Holmes built Theranos, a blood-testing medical device, in absolute paranoid secrecy.
She fundamentally bypassed the stage gate process. In the medical field, the gates are peer-reviewed studies and rigorous open validation of the underlying chemistry. She refused to let independent scientists look inside the machine, citing the fear of intellectual property theft.
She used the idea secrecy debate from segment 1 as an excuse to avoid validation.
And because she isolated the product from the friction of reality, they ended up with a physical device that literally violated the laws of physics and fluid dynamics. They tried to brute force a physical reality through sheer willpower and corporate secrecy.
The result was a massive failure in physical validation, immense regulatory fraud, and a catastrophic collapse that directly endangered human lives. It is the ultimate proof that you cannot MVP a product that requires fundamental scientific breakthroughs. The science must be validated before the product is even scoped.
This tension leads to a fierce debate in the startup community, heavily referenced in the text. The when-to-launch debate. Reid Hoffman, the founder of LinkedIn, famously said, "If you are not embarrassed by the first version of your product, you've launched too late." Do you agree with that? It seems dangerous.
The consensus in the digital consumer software space leans heavily toward Hoffman's view. Getting real, harsh behavioral data from actual users is infinitely more valuable than preserving the founder's ego by polishing a feature no one wants. However, as Theranos proves, context is everything.
Right. If you are building a medical device, an autonomous vehicle, or even a piece of financial infrastructure where failure means losing someone's life savings, you cannot launch an embarrassing, buggy MVP. Safety and security must be polished to near perfection. The domain dictates the definition of viable.
Okay, so we know what features are going in, we know our scope, but what is the actual foundation we're building this on? We need to look at the structural reality of the product, the architecture, and the unit economics.
For digital products, this structural reality is the code architecture. For physical products, it's the supply chain and manufacturing economics. Let's tackle the digital foundation first. The sources walk through a critical framework called the build versus buy decision matrix. What does that mean for a new technical team staring at a blank screen?
It means you should ruthlessly avoid reinventing the wheel. If you are building a SaaS product, a core function is processing credit cards. Do you task your engineering team with writing a custom payment gateway from scratch, dealing with banking regulations and PCI compliance?
Absolutely not. You use Stripe or PayPal.
Exactly. You buy or rent the Stripe API. What about user login and authentication? Do you write custom password hashing algorithms? No, you use Auth or Firebase. The decision matrix forces founders to identify their core intellectual property, the unique value they are providing to the user, which they must build. Everything else, all the commoditized infrastructure, they should buy.
This mindset leads directly into the massive industry debate between no-code, low-code platforms versus custom code.
Platforms like Bubble, Webflow, or Flutterflow allow founders to visually assemble incredibly complex digital products without writing traditional code syntax. It is the ultimate realization of the buy philosophy. It vastly accelerates the MVP stage, allowing non-technical founders to act as their own hackers.
But the debate centers on scalability. Right. If your no-code app suddenly goes viral and gets 1 million users, the platform's generic infrastructure might buckle, and you are locked into their ecosystem. Eventually, you might have to tear the whole thing down and rewrite it in custom code anyway.
That is the technical debt you accept in exchange for speed to market. The other major architectural debate in the sources concerns how that custom code is actually structured. Monolithic architecture versus microservices.
Think of a monolith, like a vintage, highly complex Swiss watch. Your entire application, the user login, the video player, the messaging system, the database, is all interconnected in one massive, tightly wound block of code.
It is easier for a small team to build initially because everything is in one place, but the risk is catastrophic failure. If one tiny gear breaks, if a bug is introduced into the messaging system, the entire watch stops ticking. The whole application crashes.
Microservices, on the other hand, are like a well-organized tool belt. You break the application down into independent modular pieces. The user login is one completely separate service. The video player is another. They communicate with each other, but they don't rely on each other to survive. If your hammer handle breaks, you can still pull out your screwdriver. If the video player crashes, the user can still log in, view their profile, and message support.
And the industry trend noted in the text is a massive shift toward this modularity, specifically serverless edge architecture and API-first product stacks. It is about decentralizing the risk and pushing the computing power physically closer to the user to reduce latency.
But let's flip the coin. Let's look at the architecture of the physical world.
The unforgiving economics of hardware.
We mentioned the BOMO earlier, the bill of materials. Optimization here isn't just about efficiency. It is literally life or death for the company.
Consider the scaling mechanics. In software, if a new user signs up, the cost to duplicate your code and serve it to them is essentially zero. The margins are incredible. But in hardware, every single physical unit you produce has a cost of goods sold, or COGS. Every unit requires raw materials, factory labor, and shipping.
The BIM dictates your absolute baseline costs. But the sources dive deeper into the gritty reality of the factory floor metrics, yield rates, and scrap rates. Let's walk through how this destroys profit margins.
Yield rate is the percentage of products that come off the assembly line fully functional, passing all quality checks and ready to sell. Let's say you produce 1,000 smartwatches. If 200 of them have defective screens or faulty batteries, your yield rate is 80%. Your scrap rate is 20%.
And here is the brutal part. You still had to pay for the metal, the glass, and the labor to build those 200 broken watches.
Exactly. The factory doesn't absorb that cost. You do. That scrap cost must be mathematically baked into the price of the 800 good units, so your unit cost suddenly spikes. Then you have to add landed costs, freight shipping across the ocean, customs duties, tariffs, warehouse storage, and finally, if you are selling in retail, you have distributor margins. The store takes a massive cut.
By the time it reaches the physical shelf, a smartwatch that costs $20 in raw boom materials might need to retail for $100 just for the company to break even.
This disparity highlights the fundamental risk difference between digital and physical scaling, often summarized as OPEX versus CAPEX.
Operational expenditure versus capital expenditure. This is a critical mental model. In the digital world, if my SaaS app goes viral overnight, I can log into AWS and spin up 10 new servers in 5 minutes. That's OPEX. I just pay a slightly higher monthly operational bill. It scales smoothly and reversibly. If the users leave the next day, I turn the servers off.
But in the physical world, virality can actually kill a company. If your physical gadget goes viral, you can't just spin up a factory. You have to authorize CAPEX.
You have to wire a tooling factory in Shenzhen, $100,000, to mill a massive block of steel into a new, higher capacity injection mold. That is a terrifying point of no return. The money is gone. If the viral trend dies 2 weeks later, or if you discover a subtle flaw in the mold's design after the steel is cut, you are holding a $100,000 paperweight.
To mitigate these immense physical risks, the sources emphasize lean manufacturing principles, specifically drawing on the Toyota production system known as Kaizen.
Kaizen translates roughly to continuous incremental improvement. It's the culture of empowering every worker on the assembly line to spot inefficiencies and suggest micro changes to reduce that scrap rate we talked about.
And this is paired with JIT, just-in-time inventory management. Traditionally, companies would build massive warehouses and fill them with 6 months' worth of components. But that ties up millions of dollars of cash in static inventory.
And cash is oxygen for a startup.
JIT completely re-architects the supply chain. You orchestrate deliveries so perfectly that the components arrive at the factory dock on the exact day, sometimes the exact hour, they are needed for assembly. It is incredibly capital efficient.
But, as we've seen in recent years, it is incredibly fragile. If one massive container ship gets wedged sideways in the Suez Canal or a port goes on strike, the entire globally synchronized just-in-time system grinds to a halt within days. Factories sit idle because they literally have no backup inventory. It is a high-wire act of efficiency versus resilience. Okay. So the product is live. The AWS servers are humming, or the physical factory is successfully shipping pallets of product. But does anyone actually care? How do we know if we are winning or losing?
Launching is just the beginning of the feedback loop. Now the product must survive contact with the actual market, and that requires rigorous, unsentimental tracking.
The sources provide two fantastic metrics frameworks to keep teams focused. First is Google's HEART framework.
HEART is a holistic way to measure the user experience: happiness, engagement, adoption, retention, and task success.
Let's break those down. Happiness is subjective. You usually measure it through in-app surveys or Net Promoter Scores. Engagement is behavioral. How often are they logging in? How long are their sessions? Adoption looks at the top of the funnel. Are new users actually signing up? Retention is the survival rate. Are they coming back week after week?
And task success is the operational metric. Can they actually complete the job they hired the product to do quickly and without errors?
The second framework is a classic in the startup world, the pirate metrics, AARR.
Coined by Dave McClure, it maps the exact chronological funnel of a user's life cycle.
Acquisition. How do they find you? SEO, paid ads, word of mouth, activation. Do they have a great first experience or do they bounce immediately? Retention. Do they stick around? Referral. Is the product good enough that they tell their friends? And finally, revenue. How do you actually extract monetary value from this flow?
Now, I know some people look at these funnels and argue that they turn human users into mere data points on a spreadsheet.
Right. It feels a bit cold. Are we just optimizing for clicks at the expense of genuine value?
That is why the sources explicitly demand a balance between quantitative data and qualitative data. You absolutely need the hard numbers, the AARR of funnel, to know what is happening at scale. You need to know that 40% of users are dropping off at the checkout screen. But the numbers will never tell you why. For the why, you need human stories.
You have to actually talk to the people abandoning the cart.
Right.
The sources point to communities like Product Hunt or Hacker News, specifically the show HN threads, as brutal but necessary arenas for this qualitative feedback.
You put your product in front of a community of cynical builders, and they will ruthlessly tear down your UI choices, critique your value proposition, and expose the friction you were blind to. It hurts the ego, but it hardens the product.
But what are we ultimately measuring for? What is the finish line of this initial phase? It's the holy grail of product development, product market fit, or PMF.
PMF is often described as a feeling, that magical inflection point where the market is pulling the product out of your hands faster than you can build it or ship it. It's when your servers are crashing from too much traffic or you are selling out of inventory instantly.
But relying on a feeling is dangerous. How do you actually measure something so ethereal? The sources cite Rahul Vohra's superhuman PMF engine to quantify it.
Superhuman is a premium email client. Vohra wanted to mathematically prove PMF, so he utilized a very specific high-stakes survey question. You ask your active users, how would you feel if you could no longer use this product?
And the multiple choice options are very disappointed, somewhat disappointed, or not disappointed.
The engine's benchmark is that if 40% or more of your respondents say they would be very disappointed without your product, you have achieved product market fit. You have transitioned from a novelty to a necessity in their lives.
But even more than surveys, the sources highlight one behavioral metric above all others as the ultimate truth teller: the pulse check of a product's survival.
Retention curves.
If people see a flashy ad, download your app, use it once, and never return, your retention curve drops off a cliff to zero. It doesn't matter if you have 1 million downloads or brilliant marketing, you have a fundamentally leaky bucket.
A flat, stable retention curve, meaning that a specific cohort of users who sign up today will still have a predictable percentage actively using the product a year from now, is the only baseline for a sustainable business. If retention doesn't flatten out, you do not have PMF, no matter what the revenue looks like today.
I want to share a brilliant story from the text about validating this kind of demand and finding PMF before building the automated backend. It's the DoorDash Stanford story, and it is the perfect bookend to our Warby Parker example.
It perfectly illustrates testing the core mechanic.
The founders of DoorDash, sitting in a Stanford dorm, wanted to test if college students would actually pay a premium for local food delivery. The standard approach would be to spend 6 months building a complex app, integrating with restaurant point-of-sale systems, and writing routing algorithms for drivers.
Which is massive CapEx and effort before knowing if the demand exists.
Instead, they literally walked around Palo Alto, collected paper menus from local restaurants, scanned them as PDFs, and put them on a painfully simple web page with a phone number. The site basically said, call this number to get this food delivered.
There was no app. No routing algorithm.
When a student wanted food, they called the number. The founders would answer the phone, write down the order on a notepad, physically drive their own Honda Civic to the restaurant, pay for the food with their own credit card, and deliver it to the dorm. They manually executed the entire logistical backend.
And by doing so, they realized the demand was off the charts. They were overwhelmed with calls. They achieved product market fit with a static web page and a car. Only after they validated that students would eagerly pay the delivery fee did they sit down to write the complex code to automate the logistics they had already mastered manually.
It is the ultimate lesson. Validate the behavior, automate the execution. Which brings us to the endgame, the final phase outlined in our sources. Once you hit that magical product market fit, how do you pour fuel on the fire? How do you scale it, keep people hooked, and structurally manage the immense liabilities of a mass market product?
This is where we transition from creation to governance and distribution.
The text introduces a fascinating, slightly controversial psychological framework for digital engagement. Neil Eel's hook model. How do products build actual habits?
The model is a four-step cycle: trigger, action, variable reward, and investment.
Walk us through how a company engineers this.
It starts with a trigger, an external prompt. Maybe it's a push notification on your phone saying someone tagged you in a photo. That prompts the action. You tap the notification and open the app. Then comes the crucial psychological mechanism, the variable reward.
This is the slot machine mechanic.
Precisely. When you open that social media feed, you don't know what you are going to see. It might be a boring update from a distant relative, or it might be an incredibly funny video. That unpredictability, the variability of the reward, creates dopamine spikes in the human brain. It is highly engaging.
And the final step is investment.
Before the user leaves the app, the product prompts them to make a tiny investment. Leave a comment, upload their own photo, or curate a playlist. This investment makes the product more valuable to them personally, and crucially, it sets up the next trigger. Their photo will get a like, which sends a new push notification, starting the cycle all over again.
This cycle builds inherent network effects, and that is the engine behind a massive trend in software, PLG, or product-led growth.
Traditional software relies on sales-led growth. You hire a massive team of salespeople to take executives to dinner and convince them to buy a $1 million software license. PLG turns the product itself into the primary driver of customer acquisition.
The sources highlight Notion as the ultimate case study here. Notion is a workspace and note-taking platform. But they didn't grow to a multi-billion-dollar valuation just by running Facebook ads or hiring enterprise salespeople. They grew because they enabled their users to build highly customized templates, budget trackers, complex project boards, university study guides, and easily share those templates online.
They facilitated a user-generated template marketplace.
Right. So users became evangelical. They were incentivized to share Notion with their friends, colleagues, and massive YouTube audiences just to show off the cool systems they had built. The product became its own viral distribution engine.
Now, while digital products can leverage the frictionless virality of TLG, the sources remind us that physical go-to-market strategies are much heavier. If you build hardware or CPG, you are facing a different set of distribution channels. You have D2C, direct-to-consumer e-commerce, shipping boxes from a warehouse directly to the user, like Warby Parker.
Or you have omnichannel retail, which involves the brutal fight for physical shelf space in big box stores like Target or Walmart.
Or B2B industrial sales, where you are selling heavy machinery or medical devices through multi-year, highly relationship-driven sales cycles.
And as you scale those physical products to millions of units, quality control transforms from a feature into an existential necessity. The sources unpack PLM, product lifecycle management. This is the rigid governance of the physical world.
It involves implementing strict industrial standards like Six Sigma.
Six Sigma is a statistical term, right? It essentially means engineering your factory processes so tightly that you have a defect rate of roughly 3.4 errors per 1 million opportunities.
It is the pursuit of near perfection at scale. They utilize frameworks like DMAIC: define, measure, analyze, improve, control. Alongside total quality management, these systems ensure that unit number 1 million, rolling off the assembly line, is manufactured to the exact same microscopic tolerances as unit number 100.
Because if you fail at that governance, you face a crisis. And I want to spend a moment on the dark side of design and governance that the sources touch on. When things go wrong, or when products are designed maliciously. In the digital world, this manifests as a crisis of ethics.
Specifically, the use of dark patterns.
Dark patterns are UI choices intentionally designed to trick or manipulate users. We've all seen them. Hiding the unsubscribe button in microscopic light gray text at the bottom of an email, or forcing a user to call a customer service hotline and wait on hold for an hour just to cancel a subscription they signed up for with one click online.
It is using the psychology of cognitive load, maliciously intentionally adding friction to behaviors the company wants to prevent. The sources emphasize the antidote to this: privacy by design, architecting ethical constraints, data protection, and GDPR compliance into the fundamental core of the product, rather than treating them as annoying legal hurdles to slap on at the end.
But the stakes of a crisis in the physical hardware world are exponentially higher. The sources offer a fascinating contrast between two massive hardware recalls to illustrate how the nature of the product dictates the survival of the company. Let's look at the Samsung Galaxy Note 7.
The infamous exploding battery crisis.
It was an absolute disaster. The phones were literally catching fire on airplanes. Because this was a fundamental hardware flaw deep within the chemical engineering and physical layout of the battery, there was no quick fix. Samsung had to execute a massive global physical recall. They had retrieved millions of dangerous devices from consumers' pockets. It cost billions of dollars and caused immense, long-lasting brand damage.
It was a purely physical crisis, and it required a purely physical, immensely painful solution. Now contrast that with how Peloton handled their own hardware crisis.
Peloton had a tragic issue with the physical design of one of their treadmills, which led to injuries and required a major hardware recall.
But the business survival dynamics were entirely different. Peloton is not just a hardware company. They have a massive recurring revenue software model tied to the digital content, the workout classes. During the long, complex process of sorting out the physical hardware recall and redesign, they were able to maintain their relationship with their users through the software ecosystem. Users could still take classes on the app using other equipment. The digital subscription buffered the financial and reputational blow of the hardware failure.
The software acts as a safety net, and it highlights the modern luxury we discussed earlier: over-the-air, or OTA, updates. If a modern EV manufacturer finds a flaw in the braking algorithm, they don't have to orchestrate a global physical recall, forcing millions of people to drive to dealerships. They literally beam a patch from space to fix the cars in their garages overnight.
It is a profound shift in risk management. The hardware becomes a vessel, the software is where the agility lies.
And looking forward, the sources touch on the future-proofing of this dynamic, noting massive global regulatory shifts around AI governance. As products become more autonomous, as the algorithms make decisions without human input, the liability of product design is shifting. We aren't just designing tools anymore, we are designing digital agents.
The boundaries are completely dissolving. The rigid line between the physical object, the software that runs it, and the artificial intelligence that directs it is disappearing.
We have journeyed through an absolutely massive landscape today. We started by throwing away our great ideas and hunting for unarticulated user friction. We learned to interrogate our users' past behavior with the mom test, avoiding the Juicero trap of building solutions in a vacuum.
We examined the necessity of the 4-week dating sprint to align the hacker, hustler, and designer, preventing toxic equity battles. We mapped blue oceans to avoid crowded markets, and we stared down the immense regulatory and safety cliffs of physical hardware, utilizing FMEA to mathematically predict failure before cutting metal.
We look at the psychology of cognitive load, learning how Slack pivoted away from a video game to solve workplace friction. We prototyped everything from napkin sketches and AI-generated code to CNC machine parts, surviving the brutal DVT drop tests.
We forced discipline on our roadmaps using the ICE and Moscow methods, learning from Buffer and Warby Parker how to manually validate demand without massive capex, and learning from Theranos what happens when you isolate a product from scientific reality.
We broke down the architecture of build versus buy and the terrifying realities of factory scrap rates and capex. We measured our success with pirate metrics and retention curves, realizing that product market fit isn't a feeling, it's a mathematical baseline of survival. And finally, we looked at how to scale using the hook model and product-led growth while governing our ethics to survive inevitable crises. It is a staggering amount of pressure to place on anyone designing their first product.
It is an immense undertaking. But I want to leave you with a final thought, looking specifically at the incredible tension we've observed today between the physical and the digital worlds. We talked about James Dyson spending 15 years in a shed building 5,127 physical prototypes just to lock in the final shape of a vacuum cleaner. And we contrasted that with Tesla's software-first approach where the car changes after you buy it.
Right.
As we move deeper into the realms of spatial computing, generative AI, and the Internet of Things, a world where every physical object you interact with has a digital brain inside it, I wonder if the concept of a finished physical product is going to completely disappear. Think about it. Will the expensive hardware you buy tomorrow just be a blank slate? An over-engineered, empty vessel packed with generic sensors, sitting in your living room just waiting for a massive over-the-air software update to tell it what its final job to be done actually is. The architecture of human creation is shifting from solid steel to fluid code.
That is a phenomenal perspective. So the next time you pick up a tool, open an app, or step into a vehicle, look past the surface interface. Think about the hidden friction it is trying to solve, the massive global supply chain required to put it in your hand, and ask yourself whether its final form is set in stone or if it is still evolving in the cloud. Thank you so much for joining us on this deep dive. Look at every product you touch today through this matrix, and we'll see you next time.